Hello, thanks for joining us for this first video in chapter 2, where we actually start talking about this relationship between structure and reactivity in organic chemistry, because this is a chemistry class and the primary concern is going to be the organic chemical reactions. And the reason why those are important, as we talked about a couple times now, biology, might say, is really important. Biology is really driven by organic chemistry, because everything that happens in biology, whether it's like a creature growing or your physiological whatever functioning or not functioning, and so you have disease, so you have medical intervention, all of those things are driven or really are collections of organic reactions of biomolecules, which are also organic molecules. And so all of that to say, the focus of this class is going to be learning about organic chemical reactions. And to start really delving into that, right, like we kind of need to review some of the fundamental kinetics and thermodynamics type of stuff that you hopefully remember from general chemistry. And then we're going to try to apply those to different categories of organic reactions we'll discuss here. And then we'll do some acid-base chemistry review, because that is sort of the foundation or often involved in many organic reactions. We'll learn about different functional groups that are involved in organic reactions. Organic reactions happen at the functional groups. Okay, and then we'll think about the most simple of those, which are the alkanes and different shapes or conformations, as we call them, that those molecules can take. So that's the plan for this packed chapter. First, let's think about kinetics and thermodynamics. That's why study them, because those are the two driving forces that drive any reaction. In other words, the reason why the universe is the way it is, and the nature is the way it is, and society is the way it is, your health is the way it is really comes down to kinetics and thermodynamics, which are the two factors that are inside the Gibbs free energy equation that hopefully you remember from general chemistry, right? In it, there's two factors that hopefully you remember. Delta H, remember, that is the enthalpy factor. And in chemistry, the easiest way to think about it is that this is about the bond energy, because in any given chemical reaction, you break some bonds and you form some bonds. That's really all that a chemical reaction is. So were the bond broken worth the bond formed, right? That's basically the transactional idea we're thinking about here. So one way to think about this is just the sum of bond energy, or bond dissociation energy, as often is called, of all the bonds broken, and you subtract from that the sum of all the bond energies, or bond dissociation energy, bond energies of all the bonds that are formed, newly formed. Is that worth the reaction? Like, is the energy benefit is the best way to think about it. And the main thing you want to think about is in thinking about this is sigma bonds are stronger than pi bonds. And of course, within sigma bonds, there's different kinds of bonds, and some are weaker than others and some are stronger, but those make for they don't make up for much difference. And so for that reason, when you just need to be able to estimate and look at a reaction and go, oh, this should be enthalpically driven reaction, and make a prediction like that. Usually all we have to think about is how many sigma bonds are you breaking and how many sigma bonds are you forming and how many pi bonds breaking and forming and stuff like that. Okay. The other factor, of course, is the entropy, right? You might remember from Jenkins, the second law of thermodynamics, everything wants to increase in entropy, everything wants to become more chaotic. That's favored, right? So in chemical reaction context, often that usually means you look at the difference, delta means difference in number of particles before and after the reaction. Okay. If the molecule breaks up into many particles, right, that's a more higher entropy, more disordered state. So that's usually preferred. That's why things tend to break down, sadly, not become more highly ordered. In the context of organic chemistry, sometimes we see ring opening and closing. When a ring opens, it becomes more fidgety and becomes more chaotic, so the entropy increases, whereas when a linear spaghetti-like molecule closes to become a ring, it's more ordered. So that's a entropically not favored situation. Okay, so let's apply that to a chemical reaction like this. And this is actually a reaction called cracking that's done in the oil refinery industry, where they take really long hydrocarbon molecules in the crude oil, heat it up really high. In the context of reaction equations, you might know that delta often means heat. This implies that there's going to be difference in temperature. That's what that means. And at really high enough temperature, hydrocarbons can break up into multiple hydrocarbon molecules. And so let's consider the kinetics, the thermodynamic factors for this. First, let's think about the kinds of bonds we have. Just to make things easier, we're just going to consider the number of sigma bonds and pi bonds. As far as pi bonds, right, it's pretty easy to see that the first molecule here only has one pi bond. There's 1, 2, 3, 4 carbon-carbon sigma bonds. Remember, double bond is made of a sigma bond and a pi bond. And there's 1, 2, 3 CH bonds here. 1, 2 CH bonds, so that's 5 CH, 6, 7 CH, 8 CH, 9, 10 CH. So total, there's 14 sigma bonds in this molecule. Hopefully that makes sense to you, and if not, pause the video and see if you can count them. In the products that we see, there's 1, 2 pi bonds, and there's 1, 2 CH sigma bond, 1 CC sigma bond, and 2 CH sigma bonds. So there's 5 sigma bonds here. And likewise, 6, 7, 8, 9, 10, 11, 12, 13 sigma bonds total in that molecule. What does that tell us? This tells us that enthalpically this is not a favorable reaction, right? Because bonds got weaker. Hope that makes sense, because basically what you did is you traded one of the sigma bonds for a pi bond, right? Enthalpically speaking. So delta H, hopefully you can guess the sign of it. That's one thing I want you to be able to do, is can you predict the sign of delta H and delta S for each given reaction? Not the actual value, but the sign of it. Is it positive or negative or about 0? So in this case, delta H should be definitely positive, right? You broke up much higher, better energy, better bonds, stronger bonds, and then you only made a weak bond, so delta H is positive. Okay. And what about the entropy? Well, entropically, we went from 2 particles to 1, which means entropically speaking, that's favorable. We went the other way. We went from 1 particle to 2 particles, right? So that means entropically, the entropy or the chaos or disorderedness increase. So delta S is also positive, which is a good thing according to the second law of thermodynamics, whereas positive delta H is not a good thing, right? Because that means endothermic, right? So what does that mean? This is an entropy driven reaction, right? And in fact, what happens is the entropy factor becomes bigger and bigger as temperature increases, and that's why heat is required. And in fact, if you go do the actual experiments and measure the delta H and delta S for this reaction, delta H is pretty bigly positive, 22.4 kilocal per mole, and the delta S is also positive with 33 calories per mole Kelvin. What does that mean? At low temperature, right, like T times positive delta S is not going to make this whole thing negative very much. But if the temperature is high enough, entropy can overcome this non-ideal delta H situation. And so, hence it's an entropy-driven reaction. Let's think about another example here. Here's a double bond or alkene molecule reaction with hydrochloric acid to give us a product, and we'll learn about this type of alkene chemistry later in the semester, but for now you just have to take my word for it that the HCl molecule adds across the double bond like this. Okay, so what does that mean? Well, that means we went from 2 particles to 1, and then we went from having a pi bond to none. So let's count the bonds real quick. In the beginning there was 1 pi bond total, and then there was 1, 2, 3, 4, 5, 6 pi bonds, sigma bonds total. And in the product, of course, there's 0 pi bond, and yet there's 1, 2, 3, 4, 5, 6, 7 sigma bonds, which means that enthalpically this is a good thing, right? You traded in a weak pi bond for a strong sigma bond, so delta H should be negative, which is a favorable thing. And then we went from 2 particles to 1, which means delta S wise this is not a good thing. Delta S went down, or entropy went down. It became more ordered, which is not as natural. So delta S wise, this is not a good reaction. So this reaction is an enthalpy driven reaction. And in fact, if you go measure the actual values, delta H for this is negative 15.5 kilocal per mole, whereas delta S is negative 31.3 calories per mole Kelvin. And of course, I'll never expect you to know the numbers, but we would expect you to be able to estimate, or not estimate, but predict the signs of delta H and delta S for each given reaction. Now, those are the thermodynamic considerations which tell you whether a particular reaction is favorable or not, or it could spontaneously happen or not. It doesn't tell you how fast something happens. Something might be thermodynamically favored, but if the kinetics is bad, it could take millions of years for the reaction to take place, and then that reaction is, for practical purposes, right, is one that's not going to happen. So thermodynamics are important, but kinetics are also important to consider, and especially because when you study organic chemistry, there might be multiple products that are possible. Right, then how do you know which product is going to be formed, or which phenomenon is going to happen more readily, right? Sometimes you can't just tell by looking at thermodynamic parameters like delta G. Delta G won't tell you which product might be favored, and oftentimes the major product, the main product that you should expect, may be determined by the kinetics instead. So what do we mean by that? Well, let's think about this sort of generic example where starting material A and B react to become either C or D product. And when you study the rate of this, right, like that just depends on the kinetic constant K, reaction rate constant K, and the concentrations of the starting materials or the reactants. Now, both of these are derived from A and B, so this part of the equation won't change for C or D, but what could make a difference is this rate constant K. How so? Well, because K, remember, is some constant times e to the activation energy divided by ideal constant and temperature. Remember that this is the activation energy. That's the energy that the reactants have to overcome to become the product, and that's going to depend on, that's going to be different for either C or D, and that's where we're going to see the difference. This in turn depends on the reaction mechanism. That means like what pathway the reaction is going to go through to become the product. Okay, so that's going to be different, and when you plot that difference in different pathways in terms of energy that they have to overcome, that's the reaction energy diagram, or a reaction coordinate diagram, as we sometimes call it. And remember, it looks like this, where the y-axis is some sort of reaction or molecule's energy, and the x-axis is reaction progress. The more towards the right you go, the reaction is progress towards the product. You start off to the left as the starting material of the reactant, and then you end up with the product. In this case, the reactants are A and B, and then we are saying there's two different products that are possible, right? Product C and product D. The reaction pathways could be like this, for example, just as an example. Oops. Not that it has to always be like this. Okay. In that case, the right? Like this is gonna be kind of a toss-up. It's hard to tell between C and D which is gonna be more favored when you do this actual reaction, reacting A and B, because energy wise, D is definitely the better product. It's more thermodynamically favored. C is not as good. But if you look at the reaction energy diagram, the reactants have to overcome much less energy to become C. So when the reactants don't have very much kinetic energy, because of low temperature, whatever, the product C might be favored. Whereas at high temperature, or when the reactants have enough energy to overcome this higher activation energy here, they might favor a much better product D in the long run. It's kind of like when you take a shortcut to get to where you want to go, you might not end up with a better product in the end. But if you invest in the enough energy here, you might end up with a much better, thermodynamically long-term better product. There's a lesson there somewhere. But this is the activation energy to get to C, right? And then this is the activation energy that you would have to overcome for D. So it's not as easy, but once you get to the product, it's more stable, better for the long term. So we would call this the thermodynamically favored product, whereas this is the kinetically favored product. It's kind of like the better shortcut product. Okay, so depends on all of this. How do you know which is going to be which? All depends on activation energy, which in turn depends on the reaction mechanism. And so for that reason, in organic chemistry, we're going to always be thinking about the reaction mechanism. And in the next video, we're going to introduce you to different types of reactions you might encounter within organic chemistry. So thanks for watching this video.